And welcome back to whatever this experiment is. I don't know what we're doing. Do you know what we're doing? I don't know what we're doing. Um, we have, I believe, actually, and it's kind of an interesting thing. We have 3 days set aside for redox reactions, which means we won't finish it this week. We will finish it just before Thanksgiving. Then we take a day off for Thanksgiving itself. And we have 2 days for 2 or 3 days, I forget, for nuclear chemistry, which is kind of interesting. We're going to talk about, you're going to understand nuclear chemistry a lot better than most people. Back in the late 80s, I suppose, late 80s, the Berlin Wall fell. And it wasn't long after that that the Soviet Union fell apart. The Cold War came to a dramatic end when Gorbachev said, okay, you win. And became a hero for saying it because everyone was tired of the Cold War. And the Soviet Union kind of fell apart and created a whole bunch of new little republics. I kind of had hoped that one of the new nations, they would have called it Kuchi Kuchi. Because that way, if there was ever a revolution, it would have been the Kuchi Kuchi coup. Anyway, these new little nations became, some of them, the most powerful nuclear nations in the world. Because when they gained their independence, the Soviet Union didn't have time to take their nuclear missiles away, which caused a little bit of a panic. Is it a problem today? Turns out it's not. And we're going to talk about why. I don't know if those missiles are still in the hands of those nations or not. Now, what the Soviet Union did not do was give them the launch codes. But even if they got them today, I mean, they could make a big mess of things, but it's really not a danger. And we'll talk about why. We are actually kind of ahead and behind at the same time. We are Schrodinger's class. Because we didn't quite get through kinetics as much as I would have liked in equilibrium. There are some things about equilibrium that I feel like we need to discuss. So we're gonna talk about that today. So we're a little behind, and yet we also have already discussed a lot about redox reactions. So at the same time, we're a little bit ahead. So we'll just kind of see. And I don't know if you've noticed this or not. I don't have lesson plans. It's not the way I teach. I walk into a class knowing where we got last time, knowing what I want to cover today and where I want to get to. I have no idea how I'm going to get from point A to point B. I'm told I'm a terrible teacher because of this. You're not supposed to just wing it. Well, guess what? I do. Somehow, and the funny thing is, last time I taught, of everyone teaching general chemistry, I was the only one who stayed on syllabus this way. The other two professors were making lesson plans and creating PowerPoints and presentations and all kinds of things, and it didn't help them. So I don't know what that means exactly. I'm just saying that it's not my style. Once you've been teaching for a while, I guess I don't know. Maybe I'm jaded. Who knows? But let's get started today as my cat is showing her butt to you all. And since she's showing her butt, it's probably a good thing that we minimize my image so you don't have to look at her butt. Today we are talking about, if you can see me, I don't even know if you can see me because I can't see the screen at the moment. Star is saying hello. Redox reactions. Let's review a little bit about redox reactions. In redox reactions, electrons are transferred from one atom or molecule or element or what have you to another. That's the importance of the redox reaction. Now, as it turns out, redox reactions are kind of what keeps us alive. It's redox reactions that our metabolism is based on. For example, suppose we have sugar. And we are going to react this with oxygen. This is not a reversible reaction. Get your nose out of my Diet Coke. Jeez, that's not good for you. This is not a reversible reaction, and here's kind of a hint. When one of your products happens to be a gas, unless you're Mick Jagger, in which case it's a gas, 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 and you still haven't looked up that song, so you still don't get that joke. That gas disappears. It's out of the reaction vessel. Therefore, because it's gone, this cannot react in the reverse because one of the reactants is missing. It's just up in the atmosphere. Yes, dear, you can be on my lap. Now, of course, this is not balanced, which means it is not a valid reaction. So let's balance this real quick. I'm not going to bother with oxygen because it exists as an element. If you recall, when you balance reactions, anytime you have something in its elemental state, you save it. It's the last thing you balance because I can put any stoichiometric coefficient I want in front of this, and it will change nothing but the oxygen. Don't put that down in your notes. Too late now. It will change nothing else. So we balance everything but the oxygen first. Let's start with the carbon. We need 6 more carbons here. We need 6 more hydrogens over here. Carbon and hydrogen are now balanced. We have, let's see, 6 by 2 is 12 oxygens. Plus 6, we have 18 oxygens on this side. Take away 6 because of the here. So 18 less 6 becomes 12, which means we need 6 of these. Is this now balanced? 12, 18, yes, this is now balanced. So now we have a balanced reaction. Now, in redox reactions, remember we talked about oxidation numbers. An oxidation number can be thought of almost like a charge, but it's not really a charge because we're not dealing with ions. But it's kind of the covalent equivalent to charge. Let's put it that way. If the question is simply, is this a redox reaction? I can tell you by inspection right away that yes, this is a redox reaction. And how can I tell that so quickly? Because if you recall, the oxidation number of any element in its elemental state is always 0. And I like putting oxidation numbers in parentheses right near. I put it in parentheses so I don't confuse it with a charge. So I put the oxidation numbers that I know in parentheses right near the elements. Oxygen is an element on the left-hand side, which means its oxidation number is 0. In a compound, it is not 0. So that oxidation number is changing. You only need one oxidation number to change in order to have a redox reaction. Because if one element is changing its oxidation number, well, there are some times where the same element will change in weird ways, but if an element is changing its oxidation number, that's a redox reaction. How do we get the rest of the oxidation numbers? Well, remember, the periodic chart is our friend. We memorized this. In a compound, oxygen always has a -2 charge. So in carbon dioxide, oxygen is -2. So this oxygen is going from 0 to -2. Actually, in 2 locations, it's doing that. If it's going to -2, now keep in mind, it's negative because it is gaining electrons. Electrons are negatively charged, so our oxygen is gaining electrons. And if oxygen is gaining electrons, and this is so important, this is so important. Remember, the world is electrically neutral. Oxygen cannot create electrons from nothingness. Those electrons have to come from somewhere. So if it's gaining electrons, that means something else is losing electrons. Okay? That's why it's redox. One thing gains, the other thing loses. If you recall the terminology, when an element gains electrons, it is being reduced. This is the opposite of what you want it to sound like. It's being reduced. It's gaining, but it's being reduced. But if you think about a number line, put this down here. Remember math class when you did the old number lines? As oxygen gains electrons, it is moving left on the number line. It's going from an oxidation number of 0 left to an oxidation number of -1. Left is a reduction. You're going to more negative, and negative is smaller than positive. So, yes, when you gain electrons, it is being reduced. But because oxygen is being reduced, it is forcing something else. We don't know what yet. It's going to be forcing something else to be oxidized. So if it is reduced, it is also the oxidizing agent. I can think of no exceptions where oxygen is anything but an oxidizing agent. But oxygen is not the only oxidizing agent. It's the most obvious. It's the one that we're most familiar with. Every time there's a forest fire, oxygen is oxidizing the forest. So it is the best known. So oxidizing oxygen, yes, it makes sense. Oxygen oxidizes. But it's not the only oxidizing agent. There are other oxidizing agents out there. But let's figure out what's being reduced. Whoa, let me throw my pen around. Hydrogen, if we look at the periodic chart, remember there are only a few elements that we really memorized the charge for, the oxidation number. Hydrogen is one. Hydrogen is always +1. And remember, any compound must be electrically neutral. Right? Covalent compounds are always electrically neutral. Well, if you have a polyatomic ion, then it's not electrically neutral, but well. So notice that we have 2 hydrogens here, each with a +1 charge. 2 times +1 gives us a +2. Oxygen is -2, +2 and -2 equals 0. You add them up, it equals 0. The only thing we don't know is carbon. So I'll betcha that carbon is what's being reduced. Let's find out, shall we? So to figure out the oxidation number of carbon, I'm going to do it down here just to make room for myself. We know the oxidation number of oxygen is -2. We do not know the oxidation number of carbon. So here we have one carbon with an unknown charge, oxidation number of X. We have 2 oxygens with an oxidation number of -2. And that must add up to the overall charge of the species. So if this were a polyatomic ion, like phosphate has a -3 charge, we would make this equal to -3. Carbon dioxide is neutral, so this is going to be equal to 0. So in carbon dioxide, carbon has a charge of +4. What about in sugar? You know what? This is a good chance for you to pause this video. See if you can figure out the oxidation number of carbon in sugar as practice. I'm going to go ahead and do it now. Pause the video and let's see if you get the same thing that I do. Because here's how you start. Oxygen, we know, always -2 in a compound. The only exception to that is if you have a peroxide. This is not a peroxide and we're not going to worry about that. Hydrogen is always +1. I have seen hydrogen species with a charge of -1. They are very rare and certainly beyond the scope of this course. We still do not know what to do when our Diet Coke runs out. We still do not know the charge of carbon. So we set up our equation. We have 6 carbons, each with a charge of X. Now keep in mind and notice this. When we do figure out oxidation numbers, we always ignore the stoichiometric coefficient. That's just going to confuse things. So figuring out oxidation numbers, ignore that stoichiometric coefficient. We don't need it for this step. We have 12 hydrogens. And we have 6 oxygens. And that must add up to 0. Because again, this is not a polyatomic ion. If it were sulfate, SO4 with a -2 charge, we'd say it's -2. Now notice we have a negative charge here. And this makes no sense to me. What am I doing wrong? That cannot be. That is impossible. What am I doing wrong here? We have 6 carbons with an unknown charge. We have 12 hydrogens with a +1 charge, which gives us a +12. We have 6 oxygens with a -2 charge, which gives us -12. But 12 minus 12 is 0. This is wrong. I don't know what I'm doing wrong. We cannot, in a compound, we cannot have a charge. I'm sorry. We cannot have an oxidation number of 0. It is impossible. But as I look at my setup, I do not see the mistake that I'm making. I do not see my error. This is bugging me to no ends. This oxidation, this is wrong. I don't know what's wrong. But it demonstrates the principle I'm talking about. So I'm going to check on this and try and figure out what I'm doing wrong. Sometimes this is what happens in class. Every once in a while, you make a mistake. And usually you can figure it out. In this case, I'm not figuring it out. I don't see what the mistake is. But we're going to go with it because it doesn't really matter for this example. There's something wrong with that. It cannot be 0, but you can see that it is losing electrons. It is going from a negative to a positive. I'm sorry. It is going more positive. So it's losing electrons, which is, I know, correct. It's just that there's something wrong with my calculations. Because it is losing electrons, it is being oxidized. It loses electrons, it is being oxidized, which means in this particular case, it is literally being acted upon by electrons. Because it is being oxidized, it is the reducing agent. It is the reducing agent. Kim, I don't know if you were listening or not, but you just saw me make a really major mistake if you were. There's something wrong with this. I don't know what it is, but these things happen. Okay. So yes, this is a redox reaction. And these electrons in your metabolic process begin down a pathway called the ETS system. Do I have that somewhere? I wonder. Why? I'm going to look for that up right here. Now, here's the thing. Last time we were talking about catalysts and activation energy. And I think I forgot to mention this. So the reaction, let's go ahead and draw our reaction graph here. Before we do this, let's look at this. We know that if we burn something with sugar, heat is going to be given off. We know that. This is a very, very exothermic reaction. Lots and lots and lots of heat. So the reaction is exothermic. Which means our enthalpy, delta H, is negative. We know this. Our enthalpy is negative. I also want you to notice this. We have a total of 7 moles of reactants and a total of 12 moles of product. The number of moles is increasing. You're getting more moles out than we are starting with. What's more, and this is probably even more important than that, we are going from a solid to gases. Mr. McJagger, in which case it's gases. We're going from a more condensed state. In fact, we're going from the most condensed state, solid, to gases. Mr. McJagger, I'm not going to tell that joke again right now. As we go, now here's the thing. As we go from fewer to greater number of moles, as we go from fewer to more moles, that's usually an indication that we're going to have an increase in entropy. Anytime we go from a more condensed to a less condensed state, like solid to gas, that's usually an indication that we are increasing entropy. Therefore, just by inspection, just looking at those two things alone, we know that entropy is increasing. Delta S, the entropy is going to be positive. Okay, we know that. me erase my number line here. We made our point with that. Now, remember, in natural processes, enthalpy wants to be negative, and it is here. And remember, in natural processes, entropy wants to be positive, and it is here. That means that both the entropy and the enthalpy wants this reaction to be spontaneous. Well, delta H is negative. Temperature is always, always, always positive because we use an absolute temperature scale. So a positive times a positive means that this entropy term is going to be positive, but remember there's a negative sign here. So we have a negative, and we're adding a negative to another negative. So it's negative minus a positive, so it's negative plus negative. And our Gibbs free energy will indeed be negative. So that tells us that this reaction will occur spontaneously. This is a spontaneous reaction, as we expect it to be. We know that once sugar starts burning, it's going to keep burning itself. It just keeps burning. So why is it that we do not have, and this is kind of a little review, why is it that our sugar bowl is not bursting into flames in front of our eyes? You can have sugar sitting on the table on very hot days. It's going to sit there and laugh at us. It's not going to do anything. Well, that's because of the activation energy. We have our activated complex on top. We have this very large activation energy. The reason it's spontaneous is because once we provide that activation energy, once we input that activation energy, we get it back out. It costs that much energy to get up the hill. Think about pushing a car. It costs that much energy to get up that hill. Once you get up that hill, it gives us all that energy back and more. That happens. Not much we can do about it. It's just the way it is. But consider this. The energy which we need to survive is not released in a manner that is useful to us metabolically. Our body cannot capture that heat and use it for our metabolic processes. So our body adds a catalyst. Catalysts speed up chemical reactions by providing an alternative pathway. We've talked about that before. But as far as thermodynamics is concerned, it's not just that it provides a new pathway, it's that this new pathway has a new and lower activation energy. So we don't have to put in as much energy to get that reaction started. So a catalyst always lowers the activation energy. And as we saw last time, if you lower the activation energy, your rate law constant becomes becomes larger. I'm sorry, you put a smaller EA in here, you get a larger K, That larger K corresponds to a faster chemical reaction. So catalysts lower the activation energy. The catalyst that your body uses here is an enzyme. An enzyme is a little organic molecule that speeds up chemical reactions because it's a catalyst. But remember, catalysts are not consumed in chemical reactions. That's why heat is not a catalyst. Heat provides activation energy. It's not a catalyst, though, because it dissipates, it disappears. Catalyst, always there. The catalyst that breaks down sugar is called sucralose. Shoot, I forget the name. Sucralase? I forget. It has some kind of a name. Anyway, it breaks down the sugars. It's an oxidase. I think it's an oxidase. That's what it is. Because it's oxidizing sugar. It is the exact same reaction. Overall, you're starting with sugar and oxygen. The oxygen comes from respiration. And you're breaking it down into water and carbon dioxide, which you exhale through respiration. Kind of convenient, isn't it? So it's the exact same reaction, but it occurs in a different pathway. So in this particular pathway, there are a series of steps. That energy is not released all at once, like when you burn it. It is released in a series of smaller steps. And some of these steps have larger releases of enthalpy than others. So you end up at the exact same spot. These larger steps here is how your body converts ADP to ATP. Depending on the kind of food that you eat, I know enough about Kim to know that she eats quality food. She eats healthy, she eats balanced, it's good stuff. So every time she burns sugar from that good food, she creates 3 ATP molecules from every sugar molecule. I tend to eat junk. I eat crap. And here's the interesting thing. When you eat crap, like I do, I just bought some cookies from a cookie company. I still have one left. That's going to be my lunch here in a minute. These are big cookies. When you eat junk food, you form 2 ATP molecules per sugar, not 3. Kim gets all 3. She gets the full benefits of her food. I eat junk. I only get 2. So God is punishing me. But look, you're starting off with sugar and oxygen. You're forming carbon dioxide and water. The change in entropy, exactly the same. And you're starting with this enthalpy level, and you're ending at the exact same enthalpy level. The change in enthalpy, exactly the same. And if delta H and delta S are both the same, the amount of energy released, remember, the Gibbs free energy is the potential to do work. And it is exactly the same. You do not get more energy in the presence of a catalyst. You cannot get more energy out of it. All you can do is modify the way that that energy is released. But it is exactly the same, whether you burn it or metabolize it. This is also why, now keep in mind, if this were a reversible reaction, this would not be spontaneous. If we reverse the direction of this, This is not spontaneous. You can't do it. And a catalyst will never be able to make any reaction that is not spontaneous occur. A catalyst can only speed up the reaction of a naturally occurring spontaneous reaction. So what do plants do? Plants have chlorophyll. They take carbon dioxide and water and make sugar for us or for other animals. And when we eat the animals, we get sugar. Those plants are creating sugar just for us. Well, also so they survive. How does that do it? You can force a reaction to occur with the input of energy. That delta G, if you put that much energy into it, you can force that reaction to occur. And that's what happens in the chlorophyll as it absorbs light. Light becomes the energy source to create the sugar in a non-spontaneous reaction. Does that kind of make sense? So anytime you have a catalyst, and here's the key of this, catalysts cannot force reactions to occur. If it doesn't occur naturally, it's not going to occur anyway, because catalysts do not change the overall thermodynamics of the reaction. They don't change the enthalpy or the entropy or the Gibbs free energy. It's exactly the same in the presence of a catalyst. I want to talk a little more about catalysts and equilibrium in another redox reaction, but it is 10:37. Kim, would you like to take a little bit? First of all, Kim, do you have any questions about this? I hope you don't mind that I use you as an example, because I know that you eat good food. In fact, I don't know, do you mind if I tell them about Thanksgiving?
No.
You may not be aware of this, but Kim has been kind enough to invite me for Thanksgiving. And Kim and actually her husband. I want to say Dale, but Dale is Pam's husband. Harley. Sorry about that, Harley. Harley and Kim have been kind enough to invite me for Thanksgiving because they know that I'm sort of a pathetic, lonely old loser. We're going to eat lots of food and we're going to this redox reaction. As the women clean up after we eat and all of the men are sitting around the television with our belt, with our pants buttoned open because we're too full. I say this kind of tongue in cheek, but it is an indictment of the fact that in our society, we still make the women do so much work around the home while the men basically just sit around with their pants unbuttoned doing nothing. Anyway, okay, I'm getting off my soapbox. No more politicizing at the moment. Kim, let's take a break. I will see you at 10, unless you have a question. Do you have a question so far?
No, I don't.
Okay, we're going to take an 11-minute break. I will see you at 10:45.